First speaker here, Parker Ziegler. He's at Berkeley and co-authors at Berkeley as well. And Parker's going to talk to us about fast direct manipulation programming with patch reconciliation correspondence. Thank you, Parker.
All right, thanks so much. All right, so good morning, folks. My name is Parker Ziegler. I'm a recently minted PhD candidate at the University of California, Berkeley. And my research focuses on bridging the gaps between graphical user interfaces and programming languages to build new kinds of interactive systems for working with data. And this paper, which is joint work with my collaborator Justin Lubin and my advisor Sarah Chasins, is one critical step towards that broader research vision. So the original motivation for this paper stems from this years-long journey I've been on to build a practical direct manipulation programming system for developing interactive maps, which are these very rich graphics that are increasingly essential to data reporting in today's newsrooms. So let me show you what I mean by a direct manipulation programming system. So these are programming environments that allow users to edit not only the program, but also the output produced by that program using these familiar interactions from direct manipulation interfaces. And then simultaneously, the system is responsible for synthesizing some kind of program transformation to capture those output modifications. So what you're seeing here is the actual system that we built called CartoKit, where I'm in here manipulating this output map, and the system is modifying the corresponding JavaScript program in real time. And I got really excited about these kinds of tools after doing some observational research with data journalists, climate scientists, social scientists, all of whom work with geospatial data. And from observing these domain experts, I found that many rely very heavily on direct manipulation interfaces for their exploratory data analysis and visualization, but eventually almost always need access to a program to support future customization or replication of their work. And so ever since, I've been really excited about how do we unify these two into a single interactive system. Now, our primary challenge in building a direct manipulation programming system is figuring out how to synchronize the program with the output at interactive speeds. And prior systems have tended to use an approach that looks something kind of like the following. So we have some kind of GUI interaction that a user is taking to trigger this output update. That also is triggering some program update process that is handled by this procedure that we like to call patch. Patch is responsible for synthesizing and applying that program transformation. And then finally, we reevaluate the full program to produce the updated output. And we like to call this the patch eval architecture because we have these sequentially executing patch and forward evaluation steps. In general, this architecture has worked very, very well in settings where just reevaluating the program on every GUI interaction is sufficiently fast. So things like vector graphics and web pages. But when we thought about using this architecture to build CartoKit, we quickly found that it wasn't actually going to be tractable. So why is that? Well, in our context, it's pretty common to have computation over tens of thousands to millions of records. We're often running these very expensive geospatial data transformation algorithms in a resource-constrained environment like a web browser. And then we have a very heavy graphics workload in WebGL. So to give just one example, here's a reproduction of a map published in the Washington Post. The JavaScript program that produces this map takes 18 seconds to evaluate and actually fully render the pixels to the screen. And in this case, it actually makes some sense why we're computing over nearly 500,000 rows and about 1/4 GB of data, all of which has to be parsed and stored in memory. So in general, forward evaluation in this context is just going to be way too slow for an interactive system. So seeing this problem, I think naturally we might think, OK, big data, long-running programs, maybe caching could sort of help in some way. And on the surface, I think it sounds like a plausible idea, but think for just a second about what adding caching to this diagram would sort of concretely entail. So we would need some sort of cache-aware custom evaluator that could analyze the expression in the program under evaluation and determine that some prior results from the cache could be reused for a given subcomputation. And then we need some logic in our application for actually building, maintaining, and invalidating that cache based on the interactions that the user is taking in the GUI. And that is sort of notoriously difficult to get right. So again, it's not impossible to get these things right. It's just very, very hard. And if we do mess up, so let's say we do something like erroneously reuse some cached result when we shouldn't, we can get into this really nasty state where the correspondence between our program and output are actually broken. And so from here on out, every GUI interaction that we're taking in this system is seeing an inconsistent state of the program and output. And that's kind of breaking the core obligation. So in this paper, we're really focused on trying to think about, is there something simpler? How can we actually guarantee this program output synchrony without relying on full program reevaluation every single time? All right, so one observation we can make if we look at this diagram is that we're actually already applying these very small syntactic transformations to the program via this patch operation. So could we pair this with some other operation that's responsible for making semantic transformations on the output? Now, if we've taken care of updating the output directly, can we actually just cut forward evaluation out of this loop entirely? And more or less, that's sort of the key trick behind the work. So that leads me to sort of the core technical contribution here, which is the idea of our patch reconciliation architecture backed by this formal notion of patch reconciliation correspondence. So let's dive into the details of how this works. So again, we'll start with some kind of GUI interaction, but this time this dispatches this data structure that we call a diff, which really just encodes sort of the key information about the output modification the user is making. And now, in addition to our usual patch component, we have this separate reconciliation or recon function. And so we've seen patch before. Patch handles updating the program, and recon now is responsible for directly modifying the output based on that diff. So the key thing to notice here is there's actually no arrow between the program and the output. We're never reevaluating the program in this process. And so, doing that, making that process sound, relies on there being some sort of correspondence between these patch and recon functions. That in essence, the program transformation applied by patch is sort of effectively emulated by the change that recon is applying to the output. And we're going to dive in a little bit into sort of formally how we define that and how we prove that sound. But to just take one quick step back, think about how this actually changes what a system developer is doing here. It really sort of focuses their attention on thinking about, for some given program update triggered by this GUI interaction, how do I minimally update the output to bring the two into sync? And what's really nice about this framing is that we can take a lot of inspiration from two areas of the literature that haven't really been connected before. So on the left here, there's all the great work in direct manipulation programming on how to implement patch for different kinds of languages and increasingly complex GUI interactions. And then on the right, we can actually take a lot of inspiration from the incremental evaluation literature to think about how do we make this sort of small change to the output based on sort of a minimal program update. All right, so to return to sort of that core problem, the key insight of this work is really, let's pair this syntactic operation that we have for updating the program, this patch operation, with a semantic operation for directly updating the output, which is reconciliation. Okay, so I mentioned that these two things need to share some kind of correspondence. So let's dive into formally what we mean there. All right, so consider some language L consisting of the following elements. We have a set of programs, a set of output values, a semantics that evaluates programs to outputs, a set of diffs, and then this syntactic diffing operation patch, which takes in a diff in the current program and produces the updated program as output. So our goal then is to define a reconciliation function, which is a function that takes in a diff in the current output and produces some modified output, such that for all diffs, the following equality holds. And we can represent this equality visually as this commutative diagram here. All right, so let's kind of break this down step by step. On the left here, we're saying that if we first start by patching a program based on that diff to a new program P prime, and then we evaluate that to a new output V prime, that should be identical to first evaluating the program to the output and then reconciling that output based on the diff. And if showing this equality is what's going to allow us to rely on these parallel applications of patch and recon to reach P prime and V prime respectively without actually needing to run this eval step. So we actually instantiated this full framework in CartoKit, defining a notion of programs, output values, our semantics, our set of diffs, and then our implementations of the patch and recon functions. There's a lot of Greek up on this slide, so I think this is actually best understood through a concrete example. So here's a map that a user could make in CartoKit. This map consists of 3 layers, one for US counties, one for US urban areas, and one that shows the perimeters of wildland fires in the US over the past year. In CartoKit, we model this program as essentially a dictionary of layer definitions, which map a layer ID to these triples consisting of a layer type, like polygon, proportional symbol, dot density, their associated geospatial vector data, and then these style objects, which represent the visual encoding of the data on the map. And then through repeated application of our eval layer rule, we'll transform these layer definitions into actual graphical marks that are rendered on the screen. And then the union of just all of those marks is what we consider sort of our output value here, our map. All right, so now let's say that a user is going to take one of these GUI interactions. They're going to actually transform this wildfires layer to what's called a proportional symbol layer. And this transformation is going to allow them to sort of compare the relative severity of these fires in sort of a much more direct way than a pure polygon layer. So that interaction in our system dispatches this diff, the transform layer diff, that applies to this wildfires layer and includes this transform function that we'll talk about in a second. So let's see how patch is going to operate over this diff. So here's our inference rule for patch for the transform layer diff, and it can be read as follows. We'll first start by looking up the layer in the program by ID. And then we'll actually apply this transform function to produce a new layer definition, in this case for a proportional symbol layer with some modified data and a modified visual encoding. And then in the conclusion, we're just substituting that new layer definition back into the program. And so we end up with a sort of updated program on the other side. All right, so now let's see how recon is sort of operating here. All right, so here's our inference rule for recon, which we can kind of read as follows. We'll first start by creating this set, m prime, by actually mapping that transform function over all marks in the wildfires layer. So concretely, this can actually be implemented in our system as an in-place update of existing marks. And then this set, m double prime, is actually just all other existing marks that are not impacted by this diff, so the marks from the two other layers. So these can actually just be reused. They already exist in our output. And then the conclusion of reconciliation is just the union of those sets of marks. And so again, we end up with this new output value, this union of these graphical marks, the first which can be generated through an in-place update, and the latter two are just reused from the prior output. And then the proof here really just involves saying that, hey, if we had evaluated that patch-modified program we saw earlier, it would produce exactly the same set of graphical marks that were produced in our reconciliation process. So if you're interested to see all of the proof cases, they're available in the supplementary appendix of the paper. All right, so let's dive into how we actually evaluated this system. We were really curious to understand patch recon's impact on interface latency, right? How much faster does a direct manipulation programming system feel from a user's perspective in this case? So to do this, we actually re-implemented 6 maps published by national newsrooms using both our patch recon architecture and the patch eval architecture. And then for every GUI interaction required to develop these maps, we measured how much time does it take between triggering that GUI interaction and seeing the program and output sort of fully update on screen and become visible to the user. And across all 80 cases, we found that the patch reconciliation architecture led to faster updates. And the median speedup was about a 3x. We saw a 3x reduction in UI latency. In addition, there's this really nice result where we saw that longer running programs actually saw larger speedups. So we actually get more benefit from patch recon in cases where patch eval sort of takes longer and longer to run. So up here in the upper right, we actually saw a 6x speedup on a program that originally took 18 seconds to evaluate under patch eval. OK, great. So we've seen that this seems to work really nicely for our domain and language, but what controls whether we can apply this elsewhere? And there's sort of one key insight to note here, which is to look at the signature of that recon function. Right? Recon takes in diffs and values and produces an updated value. So the complexity of implementing recon is actually contingent on the user actions that a system developer makes available, the things that actually generate these diffs. But it's not actually tied at all to the underlying language. So to see that a little bit more concretely, we can think about how we might implement patch recon for a system like Sketch and Sketch, which is a direct manipulation programming system for vector graphics. So Sketch and Sketch uses an Elm-like general purpose functional language, kind of shown here on the left, and evaluates that program to produce the SVG output here. So we can imagine that a user might do something like take this GUI interaction to change the color of this circle here. And the novelty of prior work in things like Sketch and Sketch was actually figuring out how do we do that patch operation in that context, which in this case actually involves updating that let binding for color to red. But interestingly, reconciliation can actually be pretty easy here. We just need to get references to these DOM nodes and then just call set attribute to actually set their fill to red. Now, a very astute reader will notice that this does rely on sort of tagging output values with some sort of shared identifier to know that a modification to this circle here is going to impact these others. But Sketch and Sketch actually already showed how to do that with this idea of provenance tracing, and in CartoKit, we do it through the use of these layer IDs. All right, so to wrap up, I want to zoom back out and think a little bit about what's different now that patch recon is sort of in the mix. How does this change how we think about building these kinds of systems? And I think the one takeaway is that we can now actually think about applying direct manipulation programming to settings that were previously just way beyond its reach. So whether that's image processing, computer-aided design, animation and 3D modeling, any other context where we have long-running programs, data-intensive tasks, I'm really excited about how we can turn these kinds of rich interactive GUIs into sort of full-fledged programming environments. So that's it. We've presented kind of the key idea of our work in patch reconciliation correspondence and this patch recon architecture for developing direct manipulation programming systems that can scale to long-running programs. And then we actually use this to develop what we think is a very practical programming system for domain experts. So you can try out the system today at alpha.cartokit.dev. It is currently used by folks from a few national newsrooms in the United States. And if you're curious, check out the code or get in touch with me by email or Blue Sky. Thanks so much.
Thank you, Parker, for a great talk. We've got time for a few questions. I think we've got one at the front here.
Hello, Bhargav Kulkarni from the University of Utah. Thank you for the amazing talk. I was wondering, my question was how easy is it to create recon functions for something other than maps? And you kind of answered that with the Sketch and Sketch example. But I was wondering how easy was it to create the recon function? Or could I, given a patch, program, and values, can I synthesize a recon function like to use?
Great questions. I think a key thing to kind of understand about the recon function is it's more or less how application developers build UI today. It's actually not very different from how you would actually sort of build the UI. The challenge usually is that in this context, we actually have this program that we need to sort of keep updated. So implementing recon is not difficult, but kind of thinking about actually the diffs that you want to encode into your system, and both ensuring that there's kind of these corresponding patch and recon operations that can work over the diff, and this sort of proof of correspondence is sort of where the main challenge is. But recon itself is actually something that we suspect system developers just kind of already do very naturally. So yeah, I'm really excited about that sort of element of the system. Oh, I think
you have another question? Oh, we have one down here.
Oh, yeah.
It was my understanding, or correct me if I'm wrong, a diff corresponds directly to an action a user would take in a GUI. Is that correct?
Yes. So the actions that a user takes, dispatch diffs. Diffs are user defined by the system developer. So we had our particular subset of diffs that we defined in CartoKit, but they are something that are user defined. And then patch and recon are effectively sort of giving semantics to diffs. Like recon actually sort of gives semantics, and patching is sort of a pure syntactic update based on the diff.
Gotcha.
Yeah.
Okay, thanks.
Last question.
Thank you for the great talk. I was wondering if there is some kind of difficulty in the system depending on the interactions of the GUI. So are some interaction more difficult for the system to reconcile and some are easier?
Yes, definitely. So any recon action in our system that is doing any sort of geospatial transformation has kind of this challenge of both performance overhead, but also we're updating both sort of data and stylistic encodings. And certain stylistic encodings are only valid for certain kinds of geospatial data. So those are much more tricky to reason about than sort of more simple operations that you would see in Figma or Illustrator around things like colors, opacity, stroke widths, those sort of more standard things. So yeah, there's definitely sort of a difference, and a system developer kind of needs to think about like, okay, what do they sort of want to take on in terms of the complexity? Yeah.
Thank you.
Fantastic. Let's thank Parker for a great talk.